Hello, welcome to Keeping It Classless Labs. My name is Matt Oswalt, and today we're going to be talking about rapid spanning tree protocol synchronization. Now, in preparing for this video, I do want to mention that you might be asking, Matt, why are you focusing on such a very specific feature of one very specific area of one exam? Because in the grand scheme of things, the CCIE written covers many topics, ranging from not only routing and switching, but also security and other things. Why would it be prudent to take one video and focus on one very specific thing, such as not only as specific as rapid spanning tree, which is pretty specific in and of itself, but just the one way that rapid spanning tree operates. So this video is aimed at doing one thing, and that is to focus on what I believe rapid spanning tree how rapid spanning tree sets itself apart from traditional spanning tree. There's quite a few differences, and I think that if you get into the curriculum for the first time, you start to learn things like, well, there's these new port states, there's these new port roles, blah, 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 and all of that's great. Very important information to know. But I feel like rapid spanning tree synchronization is a concept that's not very well understood by those that I've talked to in terms of learning spanning tree, at least for the first time. And I feel like it's a very crucial portion of understanding spanning tree, not just for the CCIE written, but since it really does affect our current networks today, it's important to keep that in the back of your mind. And I'm a very strong believer in learning the fundamentals of any concept, because if you understand the fundamentals, then you can extrapolate sort of the higher level learning above that. So this is not going to be a very long video. In fact, I only have one more slide. There we go. So you officially have seen my entire slide deck for this video. So we're going to focus on rapid spanning tree synchronization. And what I really wanted to touch on is the fact that rapid spanning tree synchronization is RSTP's proactive way of converging the network. It's an alternative really to the old 802.1d rules, which are bound by the forward delay timers, right? So we had 15 seconds by default in a forward delay timer. A port could not forward until twice that, so 30 seconds by default, until a port could go into the forwarding state from being blocking. And that's problematic because during initial convergence, obviously that takes a while, but even when there's topology changes, you still have to wait the 30 seconds. So in addition to all of the cool little features like RSTP integrates uplink fast into its functionality, so you have these alternate ports that, root ports can if a root port were to fail, then an alternate port becomes the root port very quickly instead of waiting, and all of that's great. That is also part of what makes RSTP very quick. But I think this process of synchronization is just much less understood than all of those things, and I feel like in terms of just regular network convergence and understanding how the network converges, then it's a good thing to learn. So RSTP synchronization does this with handshakes. So in old 802.1d world, we would say, okay, we need a root bridge. And by the way, that's the same with RSTP. We still need a root bridge in RSTP, so that hasn't changed. And in 802.1d, once we elected a root bridge, that was the only switch that was sending out BPDUs. So whenever a non-root bridge would receive a BPDU from the root, it would forward it on out all of its designated ports. And essentially, whenever a switch heard a BPDU in two places, it would take the port that it would basically say, okay, BPDU A looks like you are a better cost to the root than this other one, so I'm going to block the other one, and now you're my root port. And that's all well and good, but the problem with that again is that it relies on the forwarding delay timers. So RSTP does that a little differently. First off, in RSTP, the protocol is built so that every bridge is forwarding BPDUs. So if we stop receiving BPDUs, in the old 802.1d world, it could have been any switch in the path between us and the root bridge. Because only the root bridge is sending BPDUs, the other ones are merely forwarding them along. However, in RSTP, we know that our neighbor, quote unquote, is sending us BPDUs. So if we stop receiving BPDUs on a port, we know it's that next switch that's failed in some form or fashion, or the link between us. So that's important because now we have a little bit more intelligence as to where the failure is taking place, and we also have this idea of doing handshakes between the two switches, which is used to agree on sort of a common topology, just making sure that we all we don't have to wait for the forward delay timers. We can converge as quickly as these handshakes go about. Now, it's not like I don't want to get confused and start calling this like a layer 2 routing protocol, because there's no topology table. It's not like any switch has an idea of how the network is built. They don't keep track of that, but they still use these handshakes to really speed up that convergence process. And there's a new port state, which we will explain in a second. It's the idea of a designated blocking port state. And that sounds like a contradiction, because designated ports usually are not blocking, especially in 802.1d world. But for a very short period of time in rapid spanning tree, this state does exist. So it's transitory, and it only happens for a little bit, but it's there. And we'll get to that when we get to the whiteboard. So we've got a sample topology set up here, and this is, by the way, this is very, very similar to, in fact, it's exactly like the topology that's set up in Cisco's explanation of the proposal agreement sequence. So this idea of rapid spanning tree synchronization is aimed at doing one thing, as I mentioned before, and that's at helping the spanning tree topology to reconverge quickly without having to rely on the timers. So it's very handshake based, but what does that really mean? So the first step is, obviously, we need to elect a root bridge. The root bridge election is not specific to 802.1d. We need to do that in rapid spanning tree as well. Without a root bridge, we would not know what the central point of the network was. We wouldn't know what we were trying to trace back to. So that's the first step. So the first thing the root bridge will do is, on all of its designated ports, and by the way, port 1 here is going to be a designated port. It's connected to switch 2, which is also running rapid spanning tree. The first thing it's going to do is it's going to send a BPDU with the proposal bit set. There's a separate bit in the BPDU for just to indicate that a BPDU is a proposal, which basically instructs switch 2 to begin this process of synchronization. So synchronization is a process that a switch goes through, and it looks at every switch port, and a switch port is deemed to be in sync, quote unquote. I'm doing air quotes, by the way, if it meets one of two criteria. Number one, it's discarding through some form or fashion. I don't care how it happened. It's discarding. Or two, it is an edge port. If it meets one of these two requirements, then it is in sync. And then when all the ports are in sync, we have a synchronized switch. So when we receive a proposal, by the way, we're switch 2. We're talking from the perspective of switch 2. When we receive a proposal from the root bridge, we know that before we can reply to the root, we have to place all of our ports into in sync. All of our switch ports need to be in sync. So let's just make up some use cases here. Let's say we've got switch 2, port 2 is let's say it's an alternate port, and this is actually a good use case, because let's say there's another switch over here, and that switch is also connected to the root, because we of course built our network physically redundant. So we're going to see copies of a BPDU from the root. We're going to see this switch advertising a connectivity from the root through this path, which is obviously worse, again assuming all costs are equal, which is obviously worse because we've got double the cost. So we're not going to prefer that path, but we are going to have an alternate port, because rapid spanning tree remembers ports that it blocks because of this, and it can use them as a root port if the main root port were to go down. That's why we have an alternate port. So since it's an alternate port, it meets criteria number 1 because it's blocking. All alternate ports are blocking until they're selected to be root ports, if the main root port were to fail, for instance. Let's make port 3 a designated port, because this is also connected to a switch, but that switch is only connected to switch 2 and not back to the root, so we don't need to make this an alternate port. We can make this a designated port. And then let's say switch 4 is connected to some sort of a PC. So this is definitely going to be an edge port, because switch 2 did not receive any BPDUs on this port during the process. So the only port in this scenario that isn't currently in sync, keeping in mind that the proposal port, the port that we received the BPDU on in the first place, isn't counted in all of this. So we only need to make port 3 be in sync, because it's the only one that's not meeting one of those two criteria. It's not discarding, and it's not an edge port. So in order to be in sync, switch 2 is actually going to block port 3. or put it into the discarding state to be more proper in the rapid spanning tree terminology. And this is where we get the term I mentioned earlier, the introduction of the designated blocking state. And this is why we have a designated blocking state, because again, the point of placing a switch port into sync is to make them meet one of these two requirements. So yes, it's a designated port, but it is also discarding because we've placed it into that state to be in sync. And we're gonna touch on exactly why we've done that, because when we've synchronized switch 2, and by the way, it is fully synchronized now, all ports meet one of these two criteria, we can now respond to the root bridge, and not after, or rather not before. We can only respond with a reply if we are in sync. And by replying, what we're saying is, root bridge, I accept your proposal. You are the superior BPDU, and I am letting you know it. The point of letting the root bridge know that it's the superior BPDU from switch 2's perspective is so that the root bridge can immediately begin forwarding traffic on port 1. No forward delay timers are needed. It can immediately begin forwarding on port 1 because switch 2 has guaranteed that there's no potential loops. And it's done that because it's blocked all ports that are connected to other switches, either through making sure that it's an alternate port, which is discarding, or if it's a designated port, it blocks them temporarily. So that's the reason for placing a switch port into a blocking state, even if it's a designated port, because we need to be able to guarantee to the root that from our perspective, there's no way that loops can happen. Now, of course, the whole purpose of this is to make sure that we have network connectivity, right? So we can't keep that port blocked. The next step in the process is to send a proposal of our own down to, well, we haven't named you yet. Let's name you switch 3. So the process repeats itself, and then switch 3 needs to make sure all of its ports are in sync, so block the designated ports and reply to the proposal, and now, yeah, you're the superior BPDU from my perspective, so we're good. And it fans out from there. So in maybe a more practical sense, we have a more realistic looking network, and we have a root bridge set up here, and the proposals go down immediately on its designated ports, and these switches are going to block all their ports as part of the sync process, and then the root bridge immediately begins forwarding on them. And then the process repeats down here, and it says, well, I'm going to keep these blocked until I receive a reply. I'm going to propose down here. I'm going to propose down here, and so on and so forth. So you see the fan-out effect. In fact, I think the CCNP switchbook was what the drawing in the Cisco Press book was the first one to do sort of like a pebble in the pond effect, the ripple effect, and do that, because it really is a fan-out from the root kind of a concept. Now again, the whole goal of this is that we don't want to wait on forward delay timers. By the way, this whole handshake process sounds complicated, but I guarantee it's going to happen a whole lot faster than waiting 30 seconds for simple timers to expire. So yeah, there's a lot more activity. This is much more proactive, but what we get out of this is a much faster convergence on our spanning tree topology. So that is it for today. I want to thank you all for watching. I promised I'd keep it short. Please head over to my blog. I'm going to be posting this there, and I will also be embedding this video inside a blog post for Rapid Spanning Tree. So if you have any questions, if you have any feedback on keeping Classless Labs, please feel free to reach out to me. Twitter is usually the best way to get a hold of me, and I'm at Mierdin, M-I-E-R-D-I-N, and I look forward to seeing you on the next video.